All right, so my name is Chris Holdgraf. I'm a researcher at UC Berkeley and have been working with the Jupyter project for about the last 3 or 4 years. And I've also spent a lot of time working with the infrastructure teams at Berkeley around some of our cloud-based data science environments, such as the JupyterHub and the Data 8 infrastructure. So I'm here to talk a little bit about a couple of the tools that we're using in our stack in order to enable the kinds of pedagogy that you've been learning about through these Data 8 workshops and tutorials. So first off, if anybody is interested in these slides, you can find them at this link right here. I'll leave this on for just a couple of seconds in case anyone wants to check it out. And before I go any further, I just want to recognize that even though I'm the one that's talking about this technology, the Jupyter community is quite large and diverse and spread out all over the world. It's not just at UC Berkeley. It's not just at any one organization at all. And really, all of this technology is only possible because of this much larger, broader community of people that are building the tools, maintaining the tools, providing community support, teaching other people, and just generally creating an open and welcoming community. So ultimately, thanks should go to all of these people. So a little bit about me. As I said, my name is Chris, and I actually initially got into this world via neuroscience, which was my scientific specialization when I was in graduate school. And during my time as a neuroscientist, I ended up using a lot of tools in order to accomplish the research that I needed to do. And a lot of those tools were in the sort of open source Python data science ecosystem. In particular, there was one called MNE Python, which is an electrophysiology package for neuroscience in Python. And over the years, I kind of took further and further steps into the more generic infrastructure and open source world. And now I'm still at Berkeley, but I work on a very different set of challenges and problems. So I work kind of between three different groups on campus. One of them is the Berkeley Institute for Data Science, which is dedicated to research and open source software. One of them is the Berkeley Division of Data Sciences, which is more focused around education and also does a lot of open source software. And then finally, there's been a kind of informal Jupyter at Berkeley team for many, many years now, ever since the beginning of the Jupyter project. And I've been a part of that team for about 2 or 3 years now. And so I kind of exist at the intersection of these three worlds: research, education, and infrastructure and open source technology that powers research and education. So a lot of people ask me, what is the Jupyter community when we talk about it? Is it like a product, or is it an organization? Is it a company? And it's really none of those things and all of those things at the same time. Well, it's not a company, but it is the way that I like to describe it is that it is a community of people and an ecosystem of tools and standards all around this use case of interactive computing. Moreover, Jupyter is a community dedicated to creating things that are both language agnostic and modular, and that empower people to use other kinds of open source tools. So one thing that you may have noticed is that in the Jupyter ecosystem, it's not like there is a single stack of tools that are all Jupyter. Usually what you're doing with Jupyter is using other kinds of tools, for example, packages in NumPy and SciPy or in R, but with pieces that are provided by Jupyter to just facilitate that interaction. And that's something that's really important to the Jupyter community. So let's look at an example just to sort of make this a bit more concrete. Many of you may be familiar with the Jupyter Notebook. This is the web application that made Jupyter kind of famous about 5 or 6 years ago when it was first released. For those who aren't familiar, it's basically an interactive computing environment that's structured around a kind of document or a narrative style flow. So you have cells where you can type in Markdown that get rendered as regular looking text. And then you also have code cells where you can write code in a number of different languages and then embed the outputs of running that code in line along with this linear flow of content. It's a tool that has become extremely popular both in science and education as well as in the broader kind of data science community. And a lot of people think of it as just a single application. But in reality, the Jupyter Notebook is actually a collection of modular components that are all kind of stitched together at the end for this experience that you get as an actual user. So for one example, underneath that notebook interface that you're seeing is, starting on the left, a .ipynb file, which is basically a JSON specification or a particular way to structure a data file that defines a notebook. And there are standards around what it means to be a .ipynb file. And those standards are important because they allow, for example, other kinds of interfaces to interact with and to write notebooks as well. There's also the Jupyter Server Protocol, which is a way for you to be able to connect to like a Python kernel or an R kernel or a Julia kernel that's running on your computer. So anyone can create a kernel for any language because there's a server there with a well-defined protocol for how you can send messages back and forth from the environment that the user is in. And then there are also language-specific kernels, as I had mentioned before. These can be R, Python, Julia, whatever. Basically, any author can create a kernel that defines how your behavior when you're writing code should then be run, executed, and then have the results returned back by whatever kind of execution engine you want. And probably the most popular one is the IPython kernel, which was initially created probably 9 or 10 years ago for interactive Python. And then finally, on top of all of that, you have this diverse and broad package ecosystem. Here I'm showing you the logo of the SciPy package, which is a stand-in for the sort of broader scientific Python community. And the vast majority of those packages have nothing to do with Jupyter in an official sense. They're maintained by their own communities. Some of them are quite broad. Some of them are very niche and specific. But really, all of this stuff that I've described before exists to empower and enable people to use that open source package ecosystem. And then finally, at the end of all of this, you get that notebook interface that you're familiar with, where you're actually writing your code and looking at the outputs. But the majority of the heavy lifting is being done by these modular components under the hood. And really, when you think of a notebook interface, it's largely just a GUI on top of this broader stack. And because of those individual modular components, it means that you can start to build different kinds of things off of those same components. So for example, there are actually now a number of different interfaces into Jupyter Notebooks. I had mentioned the sort of classic Jupyter Notebook interface. There's also Jupyter Lab, which is a really flexible, sort of like a sandbox of user interface that can let you interact with multiple notebooks. You can do things like dragging and dropping cells between notebooks. And there's also a pretty rich extension environment where you can start to add on new kinds of functionality to the environment. There's also the Interact project, which is a React based version of the notebook interface. It's kind of like the classic notebook interface on steroids, and it looks really beautiful and has that kind of document focus. And all of these interfaces can be built on fundamentally the same set of tools. They don't have to reinvent the stack themselves because of that sort of modular and composable and open source design of Jupyter. So why is this important in the context of education or in the context of the pedagogy that Berkeley has been working on with Data 8? Well, as I'd mentioned before, there are already a ton of really amazing tools out there for doing a lot of the kinds of things that we would want to do in pedagogy. So for performing data analysis, for performing visualization, for doing the actual research and education stuff, we have these great open source ecosystems like in the scientific Python community, or in the open source R community. For writing the documents themselves, for authoring, for creating that content, we have great interfaces like, for example, the Jupyter Notebook interface that I just described, or the RStudio coding environment that's quite popular in R. And then we also have these tools for sharing and discovery and connecting with other people, for example, with GitHub or with GitLab, which are both online places where you can store your code and share them with others and collaborate as groups. But what we don't have as administrators at a university or as educators is a really easy way to tie all of these pieces together, particularly for beginners, for people who aren't familiar with Python or R, who are just getting started. It can be quite a big lift to ask them to set up all of these pieces in the way that makes the pedagogy most effective. Moreover, beyond just setting the environments up, it's difficult to then find the right way to interweave it with the pedagogy itself. So how do you actually teach using these tools? How do you do new kinds of things because you have this open source ecosystem or because you have these online repositories where you can share your code with others? And then there are also a whole host of problems around making these kinds of environments available to newcomers, making them remote friendly, which is something that we all care about quite a bit right now in the world of COVID. And another, which I think is really important, is making them available and accessible on any kind of infrastructure. We don't want to tie ourselves to a particular kind of infrastructure, be it local infrastructure that's on your university campus or cloud infrastructure that's being provided to you from a vendor. And then finally, we want to be able to do all of this with community-driven, community-supported, open source tools so that we're not relying on a single proprietary offering from a single organization. I think that it's really important that we try to maximize the sort of choice and flexibility available to us in order to accomplish these kind of data science environments for pedagogy. So I want to talk about two main technical pieces that we've been using at Berkeley and that we've also been developing quite a lot to try to get us closer to that vision. And probably the main component that you've heard of before is something called JupyterHub. And what JupyterHub allows you to do is host pre-configured data science environments on some kind of shared infrastructure. And that can mean a lot of different kinds of things, but I'll try to go over a few examples in the next couple of slides. So first of all, what's kind of a standard situation where you might use a JupyterHub? Well, say you have a collection of students or a collection of users. I'm showing those down at the bottom as little people figures. And you have some kind of infrastructure that exists remotely, that exists on the internet. So in the top right, I'm just have a dummy example of myhub.org. And that machine is just waiting there for people to come and start doing stuff on it. What you can do is set up a JupyterHub on that machine in the cloud. And that JupyterHub basically provides remote access to whatever resources and infrastructure exist on that machine. So users can access that JupyterHub at your example URL, myhub.org in this case, and they can get their own Jupyter sessions that allow them to run their own code and do whatever it is that they want to do. You can define a number of different kind of environments for that JupyterHub, so things like the language that people are running once they log in. You can also control things like the user interface or the environment that people get once they're running their actual code. And that can even go beyond these kind of Jupyter environments or RStudio environments. At Berkeley, we've gone so far as to just have a full desktop available for people running on Linux so that they can open their own applications as they wish. If you've got content for the course online in a repository like GitHub or GitLab, JupyterHub can be configured to pull in that content as needed and then distribute it to users so that they can use it very quickly with, for example, just the click of a button. And then this is another kind of interesting space that I think we're really starting to push the boundary of. If you have a really complex amount of computation or of data on this cloud infrastructure of yours, JupyterHub can also be used to provide access to that computation or that data. So for example, even if a user has a full Jupyter environment set up on their laptop, there's still some stuff that laptops are just never going to be able to do. So if you're, for example, a machine learning person and you're going to fit a model that would take 3 weeks to run on your laptop, really what you want to do is be able to leverage some kind of scalable cloud architecture or like an HPC high performance computing infrastructure. And JupyterHub can do that as well. It can basically provide gateway access to these resources that would otherwise be inaccessible to people. And then finally, and this is kind of an important piece, JupyterHub can also handle authentication for you. So you can connect JupyterHub with a number of different authentication mechanisms that universities might use. And as a result, JupyterHub will know who a student is or who a user is when they log on. And they'll let you do things both around providing them particular kinds of resources that student might need. That also allows them to persist their data and their sessions over time. So they can save their work, log off, come back on, and then return to what they were doing before. So as I mentioned, JupyterHub is open source. It's community driven. You can join the JupyterHub team if you wish. We have meetings once a month, and anybody is welcome to join them. It's highly customizable and configurable. It really tries to be as agnostic to the workflow or to the infrastructure as possible. You can use it for both really large numbers of users and really small numbers of users, as well as for both very, very complex and very, very simple data science workflows. And I'll get into some of that in the next couple of slides. And then finally, I want to again emphasize one of the key goals of JupyterHub is to be completely vendor, platform, and infrastructure agnostic, meaning you can run it on your own laptop if you wanted to, or you can run it on a fancy scalable cloud infrastructure that's provided to you by one of the cloud providers. We want you to have that choice of where you run this infrastructure, and we want the experience to be the exact same for a student, no matter where that JupyterHub is running in the cloud. So the most straightforward way to deploy your own JupyterHub is to use what we call JupyterHub distributions. And these are kind of like pre-configured JupyterHub setups that have several decisions made for you already that are fit to a particular use case or to a particular niche. The other thing that these distributions have is a lot of documentation for how to get up and running with these JupyterHubs. And the two flavors that I'm going to talk about here are, one is called JupyterHub on Kubernetes, and the other one is called the littlest JupyterHub. And these roughly map onto large scalable use cases and more straightforward, simple, but more lightweight use cases. So first I want to talk a little bit about JupyterHub on Kubernetes. So for those of you who aren't familiar, Kubernetes is an open source framework for managing cloud infrastructure. And JupyterHub on Kubernetes allows you to deploy JupyterHub and manage all the user pods, the environments, all this kind of stuff on a flexible cloud cluster running on Kubernetes. It uses something called Docker to define the student environments. And basically what that means is, as an administrator, you get to define the environment that students have access to by creating something called a Docker image. And when students log on to this Kubernetes cluster via a JupyterHub, it connects that environment with their session so that they get, whatever packages you've already installed or whatever data sets you've already installed. They just immediately have access to that. Kubernetes is that infrastructure, that framework that manages all of the cloud computers, requesting resources, getting rid of resources, stuff like that. And again, a big part of this is scalability and flexibility. So if the cluster is really being hammered, it can grow. And if it's not being used, then it can shrink. And then again, I should reemphasize, one of the key parts of Kubernetes is that it's an open source framework that works across all of the different cloud providers. So you can run a Kubernetes cluster on any of the major cloud providers, or you can run it on your own hardware as well. So how does this generally work? Well, I want to define just a couple of quick terminology points to help you follow along. A Kubernetes cluster is basically the whole shebang. It's all of the cloud infrastructure that you're managing for the purposes of providing these environments to your students. A cluster is generally a collection of nodes, and you can kind of think of nodes like a computer that you are paying a cloud vendor for. So a node is sort of like a machine, and that's usually the unit that you're going to be billed for. So the more nodes you have and the more high-powered those nodes are, the more you're going to be paying for the cloud provider. And then finally, pods in the context of JupyterHub are generally mapped onto individual user sessions. So when a user logs on to a JupyterHub on a Kubernetes cluster, a pod is created for them, and that's kind of a self-encapsulated little environment that user has access to. So each node can take a certain number of pods, because users are guaranteed a certain amount of resources available to them, like say 2 gigs of RAM and 1 CPU. And that means that when nodes get full, we need to request more. The other thing that you can connect to are things like user storage. So that's how you can persist the user's work over time, as well as different kinds of environment images. So if you want students to have access to both an R environment and a Python environment, you can create both of those images, and you can provide users the option of selecting between them. So let's say a user logs on to a JupyterHub that already has a couple of users here. We can see the node on the right has 3 users and the node on the left has 2 users. When a user logs on to the JupyterHub, it first asks the nodes, hey, how many users do each of you have? Does any node have extra space? And if so, it will move that user to one of the nodes that has space. It'll create a new pod for that user, and it will then connect that user's storage and the environment image that you've set up for the JupyterHub and place it on that node. And if we notice here now, each node has 3 users, so each node is now full. They don't have the capacity to bring on any new users. So if another person goes to the JupyterHub and logs in, it's going to trigger basically the creation of a new node. So Kubernetes will request from the infrastructure provider, hey, we need a new machine because we're full. That machine gets created. Once it's created, the same process happens again. A user pod is created, the storage is mounted to it, the environment is mounted to it, and now we have a cluster with 3 nodes instead of 2 nodes. So the inverse happens as well. As those users log off and their pods are deleted, eventually nodes will be what's called culled, or basically deleted. So that node is removed from the pool of active nodes, and that means that you're not paying for it anymore, which is a really good way to keep your costs down. And so this kind of scalable infrastructure, this scalable Kubernetes-based architecture, is the thing that makes it possible to run a course like Data 8, which literally has upwards of 1,000 students involved in it. Those students log on often in unpredictable ways. Sometimes they all log on at once, like right before a course exam or right before a project. And sometimes there's more like a steady background hum of people logging on and off, but in general, not a whole ton of people on the cluster all at once. And by using Kubernetes, we can basically flexibly grow and shrink the cluster as needed to make sure that we're only paying for the resources that we need to for the course. And this helps make it a cost-effective way of running this infrastructure in the cloud. Okay, so what's on the opposite end of the spectrum from this fancy Kubernetes-based JupyterHub? The littlest JupyterHub basically takes the same approach, but it applies it to only running on a single virtual machine in the cloud. So in the language of Kubernetes, it's sort of like a single node. This is much easier and more lightweight to set up. It's basically just a helper script and a collection of short guides to help you deploy a lightweight JupyterHub on different kinds of VM providers. It's much less complex than something like Kubernetes because it's less scalable than Kubernetes. But that also means that it's much easier to, for example, ask for a VM across any different cloud provider. Getting a bare bones VM is pretty much one of the most standard things that you can get from any cloud infrastructure provider. And so it's both easier to set up and it's easier to maintain than something like a Kubernetes cluster. So to visualize this a little bit, if you remember in Kubernetes, we had a whole number of nodes. We had user pods on those nodes. The number of nodes could grow and shrink inside of the cluster as needed. With the littlest JupyterHub, we basically have a single computer that we have access to. And that one computer handles authentication. It has all of the environment installed on it. It doesn't use something called, it doesn't use Docker because the environment itself is literally just installed on the computer like it would be on your own laptop. And the storage itself is also installed on that computer. So it's basically like a bunch of users having access to a single machine that they happen to access remotely rather than locally like on their own laptops. So this is more suitable for things like if you have a smaller course, say 30 or 40 students, or even a really small team like 3 to 5 team members, the littlest JupyterHub might be a better option because you don't need that extreme scalability and flexibility of Kubernetes. And you can set up a JupyterHub that gives you much more kind of quick access, and you can be a little bit more nimble about creating it. You can use it for a couple of weeks, and then you can just get rid of it without wasting a bunch of time in setup and maintenance and whatnot. So just really quickly, as a comparison between these two distributions, these two options of JupyterHub, 0 to JupyterHub for Kubernetes uses, as I mentioned, a Kubernetes cluster. It's much more scalable and it's much more complex as well. So that means that it requires more cloud-based skills, more expertise in that area, or more of a willingness to kind of grind through some of these issues and learn if you want to run on Kubernetes. The littlest JupyterHub, on the other hand, uses a single, more lightweight virtual machine that is much easier to request and much easier to maintain running in the cloud. So it's faster and it's much more lightweight. It's much easier to set up and use, but that also comes at the cost of it has more limits of what a single VM can do. You're not going to be able to run 1,000 students on a single VM unless you want to pay for a really, really expensive virtual machine that has no scalability. And it's also a little bit more difficult to set up with really complex or extreme computational or data needs as well. So this is just a total, back of the hand rubric, but a general rule of thumb is if you have more than, say, 60 students, or if you have, say, non-trivial or more complex computational needs or data needs, then Zero to JupyterHub on Kubernetes might be a good option. On the other hand, if you have a more straightforward course or team that's a little bit smaller, that needs like a good CPU but doesn't need a fancy GPU-based scalable cluster or whatever, then the littlest JupyterHub might be better for your situation. Okay, so once you have this infrastructure that's running in the cloud that can provide remote access and interactive computing environments for all of your students, how can you then connect that interactive environment with the actual content of your course? And this is another thing that Data 8 has been kind of an interesting way to pioneer some technology for. And one of the main tools that Data 8 uses to do this is something called Jupyter Book. What Jupyter Book lets you do is build an online book from a collection of Jupyter notebooks and Markdown. Basically, what it lets you do is, say you have a folder that's got a bunch of Jupyter notebooks, it's got Markdown files, it's got the actual content for your course. And oftentimes that collection of files will live in something like a GitHub repository. Oftentimes what you want to do is present that material to a student or to any user in a more accessible, traditional way. And a common way to do that is to just use a website. You don't want students to have to fire up a Jupyter server or log on to a JupyterHub just so that they can read through the content for that day. And also a lot of times content isn't really meant to be run in a live Jupyter environment, but you want that content to live alongside other pages that do. And Jupyter Book is a good way to make that really easy and beautiful to read through, and then to provide connections to something like a JupyterHub so that if students want that more complex interactive computing environment, they can access it via your Jupyter Book. So as you can see on the right, a Jupyter Book has what many would consider to be a pretty standard structure for a book-based website. You have a table of contents on the left. Each of those pages represents either an IPyNB file or a Markdown file. You have each page's content in the middle, and as you can see here, this is basically like the structure of a Jupyter notebook, and that's because this page was built with a Jupyter notebook. So you have Markdown areas, you have code cells, you have outputs from those code cells. And then there are also some more kind of document-focused features, like there's a sidebar where you can add margin content and asides and things like that. Those are user interface elements that don't exist in the traditional notebook environment, but are often very useful when you're, for example, writing a textbook or you're writing a more traditional scholarly artifact. So there are a couple of interesting ways in which Jupyter Book then makes connections with the broader Jupyter ecosystem and tries to empower you to kind of create exactly the experience that you want from a user's perspective. One of those examples is something called launch buttons. And what launch buttons do is they connect your Jupyter Book page, which is just a static web page. They connect that page with an online interactive environment that the students have access to. So in this example, again, underlying this page is an IPyNB file. It was built with that file. And the person navigates to the top of the page. They click on this Binder link. Binder is a service that can run online that provides interactive computing environments. And when they click that link, they're taken from the static version of the page to a live interactive version of that page running, in this case, on Jupyter Lab. And this is something that the Data 8 textbook uses quite a lot. For example, we run at Berkeley a JupyterHub called the Data Hub for all of the students. And many of the textbooks that we use have these interactive links at the top. And when students click them, it will take them to their session in the JupyterHub, in the UC Berkeley Data Hub. And that way you can kind of blend the line between a fully static website that you can easily click on just as at a URL versus this much more complex interactive computing environment running in the cloud on a JupyterHub. You can also have some degree of control over the content on your actual pages. So I mentioned before, there are some things that you might want to do in that final book-based version of your content that don't make sense to do when you're writing that content in a Jupyter Notebook interface. One example of this is oftentimes you want to either hide certain kinds of content and ask students to click on a button to see what's inside. So many people use this for things like question and answer cells so that students can try to think about the answer before they actually see something. Sometimes you also want to hide the code that's used to generate an output. So maybe the code itself isn't really relevant to what you're trying to teach someone, but you just want to show that image itself. And JupyterBook has the ability to let you tag things that should or shouldn't make it into the final page that students are viewing. And then finally, this is a relatively new feature, but it's a pretty interesting one. You can actually generate outputs in one code cell or in one page of your book, and then insert those outputs into a different part of your book, into the actual content sections of your book. So for example here, say you've built a histogram and you've run a permutation test, and you have both a plot and some numbers that came from running that permutation test. Say you have like a confidence interval. You can generate those numbers in that plot just with regular old Python or NumPy or whatever. And then in your content later on, you can say, I want you to insert the result of this variable into this location in the text. And so on the right, you can see what that might look like. So here we've pasted a figure from generating that image with matplotlib. And we've also inserted in line with the text the number associated with running this confidence interval. And you can even do some wacky things like inserting tiny little inline figures along with your text. So this basically lets you separate out parts of your content that are running and generating the code, which are often quite messy, versus the parts of your content that are more meant for readers to really look through from top to bottom, that can read more like a narrative. It sort of helps you declutter the messy computational parts of your content and the more narrative focused parts of your content. So if you're interested in looking at an example of this, I would check out the Data 8 textbook. Many of you may have already seen this already, but the Data 8 textbook itself is built with JupyterBook. You can find it at inferentialthinking.com. And it has a lot of interesting use cases for how you can, again, kind of interweave computation and use that as a narrative tool to help teach people about data science and about the statistical concepts that are covered in Data 8. So the Data 8 textbook is online. It's freely available for anyone to see and to use. It's licensed so that you can reuse it in your own content. I think it's CC BY non-derivatives license, something like that. All of the content of the Data 8 textbook is written in Jupyter notebooks, so they're all runnable on their own, although they are displayed to students as a Jupyter book. So students will often read this kind of static website version of the content, and then they'll click through to go to a live interactive version of the Jupyter notebooks. And again, the stack of tools that's used to both build this content and host it online is completely open source and community driven. Again, kind of benefiting from that modular composable ecosystem that I mentioned at the beginning of this talk. Okay, so I've covered a couple of different pieces, sort of core pieces of infrastructure in the Jupyter ecosystem at Berkeley. So what are some things that you may want to do next if you're interested in either adopting this at your own institution or pursuing these kinds of topics a bit further? So the most common question that we get from people is, okay, JupyterHub sounds great. What should I do next? Like, how should I get a JupyterHub at my institution? And what I would recommend, again, this depends a lot on what resources you have available to you, is to start out by trying the littlest JupyterHub and pilot it on a smaller or a sort of less risky group first. It'll take you a while to just learn both how to set up the infrastructure, but also how to use that infrastructure in the context of teaching in a way that is effective. And I found that it's most useful to do that if you have like a boot camp or a weekend workshop or something like that, where it's not going to be a huge deal breaker if things don't work the way that you're expecting. Use that to build up expertise and kind of learn the workflow. And then that'll also give you a better intuition for how or when you should use this infrastructure for teaching in the future. And then if you want to kind of take things to the next level and you want to either have a larger classroom or some more complex infrastructure as a part of your work, then look into using Kubernetes and the Zero to JupyterHub distribution. Again, this is often not needed for most course sizes. I think you can use a littlest JupyterHub for up to 60 to 100 students even if you wanted to. Really the only difference there is that for larger courses or for more complex infrastructure, the littlest JupyterHub will become more expensive. And that's because you don't have the flexible scalability that you have with something like Kubernetes. So, there are just trade-offs and pros and cons in both directions, but I think that the easiest way to get started is by deploying a littlest JupyterHub for your groups. Another thing to keep in mind is that there are often lots of other resources that you can leverage other than just yourself as an individual working on this stuff. So many universities or collections and communities of universities do have cloud expertise. So there are often researchers or administrators or IT people who have done things with the cloud before. Kubernetes is relatively new in this space, and the academic world tends to be a little bit behind the industry world in adopting those tools. But it's definitely becoming more common for people in academia to know about Kubernetes, to know about cloud infrastructure, and you can usually find others that can help you along the way. The other thing that you can do is seek out other open source communities or others in the kind of broader data science ecosystem for help with doing this kind of stuff. One example of this is Jupyter has a community forum at discourse.jupyter.org, which is just a place for people to ask questions about using Jupyter, using JupyterHub, deploying it at their institutions. There have been a lot of really great threads there about specifically how to use JupyterHub in education or other Jupyter tools in education. And reaching out to that broader community is a great way to both plug into an enjoyable community to be a part of, and also to learn from expertise that others are willing to share with you. And then finally, there are also other organizations out there that are willing to partner with educational institutions or research institutions in order to help them deploy this kind of infrastructure. So for example, there are a lot of consulting companies that can provide technical consultation or support for deploying this. And then there are also some vendor-specific or more proprietary notebook products that you can just access either in some cases for free or that you can purchase as a service from vendors. And it's not quite the sort of community-driven or open source solution, but it can also be a reasonable way to access these kinds of environments in a relatively pain-free manner. So finally, I want to talk about a recent effort that some of us who have been involved in the Data Hub at UC Berkeley and a few similar kinds of infrastructure efforts across the country, actually not just across this country, but across the world, have been working towards for the last couple of months. And this is something that we call the International Interactive Computing Collaboration, or 2I2C for short. So this is a very, very young, new effort to create a nonprofit organization that's dedicated to supporting and providing interactive computing infrastructure for research and education. So basically doing the kinds of things that I've just described in this talk, but as a service for universities, for research organizations, for government labs that aren't able to access, their own DevOps expertise. It's a mission and a values-driven organization that wants to be directly aligned with the goals of the universities and with the goals of the open source communities that underlie all of this infrastructure. So it basically does three things, or it will do three things. One of them is provide, manage, and support Jupyter hubs and complex interactive computing environments for an organization. So it wants to be able to do that both on any of the cloud provider infrastructure or on your own university or organization's infrastructure. So again, flexibility and choice is really important to us as open source advocates. And what we want is to create an organization that can empower flexibility and choice in accessing these environments for whatever your organizational needs are. The other thing that we're going to do is provide technical collaboration on more bespoke or more complex research projects or educational projects. So a lot of the development of Data 8, for example, went back into the JupyterHub project, required new things to be created or new tools to be developed. And that's a really useful cycle to have because it ensures that the open source tools are created directly in the context of educational use cases and research use cases. And that's another kind of pattern that 2I2C wants to be involved with. And then finally, 2I2C also wants to provide core support for the open source communities and the open source tools that underlie the infrastructure that I've been talking about here. So it may come as a surprise to some of you, but for a project as large and impactful as the Jupyter project is, it's actually in many ways a very under-resourced organization, a very under-resourced community. And it takes time and effort and people and sometimes money to both create new and interesting tools, but also to maintain those tools, to provide community support, to help grow that community, to teach others and help others learn how to use these tools. And what we want to do is create an organization that's directly in line with the goals of the Jupyter organization, the Jupyter community, as well as the communities of the open source projects underneath it, so that we can provide some core support for these tools, which is something that we've been doing for many years, but something that we'd like to formalize and make a little bit more sustainable than has been the case in the past. So as I mentioned, this is very, very new. It's basically come out of a recognition that there needs to be an organization like this, from running the Data Hub at Berkeley, from running other open source projects like the Binder project or the Syzygy project in Canada. If you're interested in this, either as an organization that might want to just purchase Jupyter Hubs as a service, or as an organization that's interested in sort of helping think about how 2I2C could accomplish this mission and what kinds of things it could do and how it could structure itself, I encourage you to reach out, and we would love to talk with you and figure out how we can make this happen. Okay, so with that, I'm going to end the main content for this. I'll leave with just a couple of links that you can check out at your own discretion. UC Berkeley has a pedagogical guide for how you can run your own version of Data 8. It covers things like how to think about Data 8, why were the decisions made the way that they were, how is teaching interwoven with the infrastructure, that kind of thing, at data8.org/0 to Data 8. And then we've also got an infrastructure guide that covers, as you can guess, some of the more technical pieces of this. JupyterHub, Kubernetes, it covers a lot of the things that I talked about in this talk and goes into a little bit more detail about what your different options are as well, at the link below just there. Both of these guides are works in progress, and so I also encourage you to check out the GitHub repositories where they're hosted, post questions, post issues, ask for clarifications. We're running all of this documentation in the same way that we would run an open source project, which is in an open, collaborative, and transparent manner. If you want to learn more about Jupyter, and particular Jupyter infrastructure like JupyterHub and the cloud and the things that I talked about here, you can check out the 0 to JupyterHub guide at z2jh.jupyter.org. That's the Jupyter distribution for Kubernetes. And you can check out the littlest JupyterHub guide at tljh.jupyter.org for a more lightweight single VM use case. You can go to jupyterbook.org to access documentation, installation instructions, customization instructions for building your own Jupyter books. And then, as I mentioned before, there's also a really great community resource in the Jupyter Community Forum where you can basically talk about whatever you'd like to in and around the Jupyter ecosystem at discourse.jupyter.org. So thanks very much for taking the time to listen to me. I'll be around later on in the week to talk at some of the panels around infrastructure and to field some questions. Don't hesitate to reach out if you have any questions of your own. You can find the links to these slides over there on the right. And I look forward to connecting with you online. So thanks very much.